Program Evaluation and Summary. This Go program is a command line application designed to demonstrate and facilitate cryptographic operations, specifically Diffie-Hellman key exchange, DHKE, with a custom, hybrid one-time pad, like encryption, and AES-GCM, Advanced Encryption Standard, Galois, counter mode, for two-way conversations. The program is interactive, presenting a menu-driven interface to the user. Let's break down its components and functionality. Animation, visual content. As this is a command line program, there's no visual animation or graphical content in the traditional sense. The visuals consist entirely of text output to the console, including main menu and sub-menus for user interaction, prompts for user input, e.g., enter message to encrypt, paste keys here, display of generated keys, base, modulus, public, shared secret, display of encrypted and decrypted messages, informational messages and instructions for the user, clearing the screen using FMT, print, 033H, 033-2J. Audio content summary. Being a command line application, this program does not have any audio content. Its interaction is purely text-based. Scene-by-scene intent, program flow and functionality. The program's main function serves as the central control flow, presenting a main menu with different cryptographic options. Initialization and setup. Intent, to prepare the environment for cryptographic operations. This involves seeding the random number generator, generating a random 12-byte initialization vector, IV, for AES-GCM, and displaying it to the user. The IV is crucial for the security of AES-GCM. Main menu loop, loopback menu. Intent, to provide a persistent interactive interface for the user to choose between different cryptographic functionalities or to quit. It clears the screen and displays the main menu options, DHKE sender functions, DHKE receiver functions, AES conversations functions, and quit. Case 1. DHKE sender functions. Intent, to guide a sender through the steps of initiating a Diffie-Hellman key exchange and then encrypting a message using a shared secret derived from it, combined with a one-time pad-like XOR operation. Key size selection. The user is prompted to select a key size, an integer z between 4 and 8, which implicitly relates to the magnitude of primes used and the maximum message length. Message input and length validation. The sender inputs a message. The program then validates the message length against the chosen key size to ensure it doesn't exceed predefined limits, e.g., for z equals 4, max message length is 200 characters. If too long, the user is prompted to re-enter. Prime generation. Build base, build mod. Sieve of Eratosthenes, n int. This helper function efficiently generates a list of prime numbers up to a given limit n using the sieve of Eratosthenes algorithm. Build base, zint, msg string, generates a slice of random prime numbers to serve as the base, g in standard DHKE, for each character in the message. The size of these primes depends on z. Build mod, zint, msg string, generates a slice of random prime numbers to serve as the modulus, p in standard DHKE, for each character in the message. The size of these primes also depends on z. Secnum equals build mod, z, a single random prime is generated to act as the sender's private key, a in standard DHKE. Calculate sender's public keys, pubnum. For each character in the message, the sender calculates their public key, base private _ key, mod modulus. These are large integers handled by math, big, int. Output keys for copy-paste, base 64 encoded. The program prints base 64 encoded strings for the generated base numbers, modulus numbers, and the sender's public keys. These are intended to be manually copied and pasted to the receiver. Input receiver's public keys, get key set. The sender is prompted to paste the base 64 encoded receiver's public keys, which were generated by the receiver's instance of the program. Calculate shared secret, share num. Using the receiver's public keys, the sender's own private key, and the modulus numbers, the sender calculates the shared secret, receiver _ public _ key sender _ private _ key, mod modulus. This should theoretically be the same as the receiver's calculation. Encrypt message, XOR with shared secret. The original message, converted to ASCII integers, is XO read, with the derived shared secret, character by character. This implements a form of one-time pad encryption, though it's dependent on the shared secret generated by DHKE, not a truly random, pre-shared pad. Output encrypted message, base 64 encoded. The base 64 encoded encrypted message is displayed for the user to copy and paste to the receiver. Loop back to main menu. The program pauses and then returns to the main menu. Case 2. DHKE receiver functions. Intent: to guide a receiver through the steps of receiving keys from the sender, generating their own public key, deriving the shared secret, and then decrypting the message. Input sender's keys, base 64 decoded. The receiver is prompted to paste the base 64 encoded base and modulus keys from the sender. These are then decoded back into numerical slices. Generate receiver's private key, BSECNUM. A single random prime is generated to act as the receiver's private key, B in standard DHKE. Calculate receiver's public keys, BPubNum. For each base and modulus pair, the receiver calculates their public key, base_receiver_private_key, mod modulus. Output receiver's public keys, base 64 encoded. The base 64 encoded receiver's public keys are displayed for the user to copy and paste to the sender. Input sender's public keys, base 64 decoded. The receiver is prompted to paste the base 64 encoded sender's public keys. Calculate shared secret, shares. Using the sender's public keys, the receiver's own private key, and the modulus numbers, the receiver calculates the shared secret, sender_public_key receiver_private_key, mod modulus. This should match the sender's shared secret. Input encrypted message, base 64 decoded. The receiver is prompted to paste the base 64 encoded encrypted message from the sender. Decrypt message, XOR with shared secret. The encrypted message, decoded to integers, is XO-read with the derived shared secret, character by character, to recover the original ASCII values. Translate decrypted message to ASCII. The numeric decrypted message is converted back into a human-readable string. Loop back to main menu. The program pauses and then returns to the main menu. Case 3. AES conversations functions. Intent: to demonstrate basic AES GCM encryption and decryption for a two-way conversation, using a randomly generated 32-byte key or a pasted key. Submenu loop, AES loopback. Presents options for key management, key, sending a message, send, receiving a message, receive, or quitting AES functions. Generate, paste AES key. The user can choose to either generate a new 32-byte AES key, using crypto, RAND for cryptographically secure randomness, or paste a key from an external source. The key is converted to a 32-character string for use with AES. Send, encrypt, message. The user inputs a plaintext message. GCM_encrypt. This function uses the generated 32-byte AES key, the initial 12-byte IV, generated once at program start, and the plaintext to perform AES GCM encryption. The ciphertext is then hex encoded and displayed. Receive, decrypt, message. The user pastes a hex-encoded ciphertext. GCM_decrypt. This function hex decodes the ciphertext, then uses the same AES key and IV to decrypt it via AES GCM. The plaintext is then displayed. Note: the GCM_decrypt function appears to incorrectly extract the nonce from the ciphertext. In GCM, the nonce is typically prepended to the ciphertext by the sender, and the recipient must separate it before calling AES GCM, open. The provided GCM_encrypt function seals the IV into the ciphertext, making it part of the returned ciphertext byte slice. However, the GCM_decrypt attempts to read non-size bytes from the received hex-decoded ciphertext, which isn't directly the IV that was used to encrypt. It should be the same IV that was used to encrypt, or extracted from the ciphertext if the sender prepended it. Currently, the GCM_decrypt function is using the global IV variable for decryption, which is only correct if that IV was indeed the one used for encryption and is accessible to both sides. For a truly two-way conversation, the IV typically needs to be exchanged along with the ciphertext, or derived in a predictable way. The code nonce, ciphertext, equals ciphertext, non-size, ciphertext, non-size, inside GCM_decrypt is a standard way to separate a nonce that has been prepended by the sender, but the GCM_encrypt function in this code passes the IV separately to AES GCM seal, meaning the IV nonce is not prepended to the ciphertext it returns. This is a security flaw in how the AES GCM is used here. Quit AES functions returns to the main menu. Case 4. Quit intent to gracefully exit the program. Key features and considerations. Hybrid approach. The program combines Diffie-Hellman key exchange for key agreement with what appears to be a custom XOR-based one-time pad for message encryption in the DHKE section and standard AES GCM for the dedicated AES section. Manual key exchange. All key exchange, base, modulus, public keys, encrypted messages, is done manually via copy-pasting base 64 encoded strings. This is highly impractical and insecure for real-world use but serves its purpose as a demonstration. Prime number generation uses the sieve of Eratosthenes to generate primes for the DHKE parameters. Math, big package, essential for handling large integers involved in Diffie-Hellman calculations, exponentiation modulo n. Security concerns. DHKE part. Custom XOR encryption. While XO ring with a truly random, unique pad is secure, here the pad is the shared secret derived from DHKE. This means it's a stream cipher where the key stream is generated via DHKE. The security relies heavily on the robustness of the DHKE parameters, prime sizes, and the true randomness of the private keys. No authentication, integrity. There's no mechanism to authenticate the sender or receiver, nor to ensure message integrity, i.e., detect if the message was tampered with in transit. Fixed private key for all characters, DHKE, the sender's and receiver's private keys, secnum, 0, and BSECNUM, 0, are single values applied to all base, modulus pairs for the message. This means the shared secret generation for each character uses the same private key. While DHKE normally generates a single shared secret, this implementation extends it across multiple prime pairs, which might be an attempt at a hybrid one-time pad, but isn't standard practice. Security concerns. AES GCM part. Incorrect IV handling. The GCM_decrypt function attempts to extract a nonce from ciphertext that wasn't prepended by GCM_encrypt. It also uses a global IV. In real AES GCM, the IV nonce is generated per encryption and must be communicated alongside the ciphertext. Reusing an IV with the same key is a critical security flaw that compromises confidentiality. The global IV is generated only once at the start of the program. Key management. The AES key generation is cryptographically secure, but its handling, e.g., direct string conversion from byte, global variable SG keycon v32, might not be robust for real-world applications. User experience. The program is designed for demonstration, requiring manual input and output of large strings, which is cumbersome but serves the pedagogical purpose of showing the steps involved. In summary, this Go program serves as an educational demonstration of fundamental cryptographic concepts like Diffie-Hellman key exchange and AES GCM encryption. While it illustrates the core mathematical and algorithmic steps, it contains significant security vulnerabilities in its implementation of AES GCM, due to IV handling, and lacks practical features like automated key exchange or message integrity checks, making it unsuitable for secure real-world communication.